Okay, hello again. Let's talk a bit about the uh, booting process of the system. And we said when we showed the MBR that we have like the program code which starts at the beginning of the MBR, and this is compiled 16-bit assembly code. This operates on real mode, as it said, or on ring 0 when we discussed the rings at the previous lecture. So this code can access a large chunk of memory to the 16-bit potential addresses in memory, and due to the 16-bit potential addresses in disk, right? Because that is the mode that it is currently executing in. If it wanted to access more, then it can change the mode that it is executing to a 32-bit or a 64-bit addressing mode. This is a very important forensic artifact in the disk because this MBR code can potentially contain malware, and MBR resident viruses or malware can persist themselves by changing this code and allowing themselves to execute every time the computer starts up. So we need to potentially make sure that this is the correct MBR code that we should have there, and it's not malware or nothing is hiding there. Now, we also mentioned here the disk signature that starts at 1B8. The disk signature, every time the operating system is mounting that disk or accessing that disk, it is persisted in log files and such. So by the disk signature, which should be kind of unique in every disk, we can infer if the user is plugging in a certain, for example, USB drive. If they plug a different USB drive, then we should see another disk signature, and we can infer what is happening in terms of which devices are, which disks are being presented to the system. Also, if we see the same disk signature, we can infer that probably the disk was cloned, maybe block by block, by some program. Okay. Then we talked about the partition entries that start at 1BE, and then we talked about where the end signature should be at offset 1FE, and the end signature should be 55AA. Now, what we're looking for when we're examining an MBR again is if we actually see the same number of partitions as we expect, if the partitions are marked active, and if they're inactive partitions that we're just not able to boot them, but they are there. If the layout makes sense for the characteristics of the disk that we see in front of us, and also if there is any free space. If there is any free space, people could actually put data in that space, and this data wouldn't be evident from the file system of any of the operating systems listed in the MBR. Now, as we said, MBR has certain limitations. Remember, there was like just 4 entries that it could have for primary partitions. So at some point, there was this was extended to something called GPT, which it's a GUID partition table. GUID means Global Unique Identifier, and this can support way more active partitions, as you can see here. And therefore, you can imagine that also can have a way bigger size, as the GPT, the whole GPT can be bigger than MBR. So it's not just 512 bytes that was MBR. It can be actually of a variable size. So it also uses logical block addressing. And here I give you the formula to get the logical block address of something if you have the cylinder head sector address of something. Okay. You are going to need the heads per cylinder value, the sectors per track value, and if you plug this in this equation, you will get the logical block address of that is used in GPT. So for compatibility, in the beginning of a GPT partition table, we have still an MBR that is still there, and I'm going to show you in the next picture. So remember, this was the MBR that takes up 512 bytes. Okay, and um, we can see here that this MBR is still preserved in the beginning of the GPT. Now, we said before, if we want to use dd'ed to acquire an MBR, this is very simple, right? We want to get the master boot record of this disk and write it on this output file. We just take one count of block size 512 bytes, and that should be enough to get us the whole master boot record over here. But to get the GPT out, since we don't know the size of a GPT, and it can potentially have way more entries, then it's not as easy as to just get a certain amount of bytes out. One trick that I use when I want to read the GPT here is like I will read the first, for example, 100 512 byte blocks out of the disk, and then by examining with hexdump, I'm going to try to find similar areas that have the exact same data, and that is the reason for that is because GPT, for redundancy purposes, it keeps a copy of the partition array further down the disk. Okay, so if I find these two identical sections, I know that these copies are, this is the primary partition entry array and the backup partition entry array, and in between I'm expecting to find before the primary partition array, I'm going to find the table header and all that stuff. Okay, so that is one trick that you can use to figure out how much you need to carve out of a disk to get the whole GPT. Now, this can be tedious to examine something with just a hex editor, in the console for some people. So there are commercial tools that, like for example, Encase, which we saw here. And these commercial tools, you can see you can see the blocks over here. You can click on a block, and then it's going to actually run a hex dump for you, in a window, so that some people feel better for that. And you can see, for example, the which cylinder something is here, and the addresses that something has, and it can also parse into this data and give you understand more about what is being examined. So, for example, it can tell you that this is a directory, a folder in Windows, and all that type of stuff. Now, this is a commercial tool. It's very expensive to get a license for this, but there are also open source tools that we will talk about, like for example Autopsy, or Guy Imager, or other tools that you can use to get still a visual representation of what's going on in these blocks. Now, let's talk a bit about other internals on a file system. So we kind of talked about inode tables, right? That can contain the inodes that will make up the files on that file system. But there are also other things like, for example, free block bitmaps. Okay, a bitmap is something that you can just set a bit, just one bit out of, not from a whole byte, just to 1 or 0, and that can tell you quickly, just by looking at this map of bits, if something is allocated, for example, or free. So to make sure that something, to make sure that something is, for example, free, you just read that bitmap, which has like 1 bit for every block, and then look at that certain bit that matches that block and see if that's set. If that's set, the block should be free, for example, right? Or it can have statistics built in. The inode tables we kind of talked about. Okay, but a thing that I want to focus your attention now is like something called a journal, and the journal is a data structure that tracks what should be happening at any given point, okay, before you actually do it. And that's more than do it before you actually perform the action. So if, for example, you are modifying a block and you want to copy 5 blocks of worth of data to some other 5 blocks worth of data, because for example you did a file overwrite, for example, it is important to write in the journal what you're starting to do when before you start doing it. Because if something happens during that operation, so for example the power goes out while you were copying, out of these 5 blocks you had only copied 2, and then the power went out in the computer, to recover the file system and make sense of the state, it would be very useful to know what was the last action that you were doing. So you could have logged on the journal, I was copying 5 blocks from here to there because this file was overwritten, right? Then you can compare the state of these blocks, both the source and destination blocks, and make sense and establish how much of that operation was actually completed and how to recover the corrupted state of that specific operation, right? So this is the idea of journaling, and modern file systems usually do some sort of journaling. So let's see again how, for example, ext3 and Windows implement journals. Okay. Here again, I'm just mentioning another example. We talked about in the previous slide about overwriting a file, but here we say, okay, what if we want to delete the file? Okay, if we want to delete the file, we want to delete the inode, right? All that metadata of that deleted file, we don't care about it anymore, right? About who the owner was or what were the permissions, right? We want to return that inode back to the free inode list so that this inode can become some other file, right? We want to change the directory entry, okay, and we want to remove that file name from the directory and that entry from the directory because that directory does not contain that file anymore, okay. And also take the actual data blocks of that file and put them back into the free list of blocks. So when we allocate another file, we can reuse these blocks. Now, I would like you to notice here that I'm not necessarily saying zero out the blocks, for example, right? That could be a decision that you make when you write your own operating system, or if you want to mount the file system with certain options that override the data with a random pattern, for example. You could do that. But by default, most file systems don't spend time to override the data with a random pattern or some pattern, right? And that means that if you allocate space for another file and you don't necessarily truncate the data out, if you now allocate space, for example, for a sparse file, you might find data that are actually in the blocks that belong to some other file, okay. Or if you just examine the blocks of the file system, then you might find data of some other file. Now let's talk a bit about how ext3, which is the kind of one of the standard now Linux file systems that you might see, implements journaling. So when you have a journal in a file system, you have certain options. You can either say I want to journal only on the metadata level. So that means what we described before. Just keep a copy of the actions that should be happening on the metadata. Don't really deal with the data blocks. But there is also an option of journaling where you can journal also based on the data that you read. So every time you read the data block, this part, the beginning of this block, kind of goes also into the journal. That can be very useful in certain forensic scenarios, right? Because you can actually find copies of the data blocks in the journal, okay. Now on Windows we have this special file here, which is it's called log file, and this is again a similar metadata type of journal. So for example, what is happening, if that what should happen in the directory entry, and all that stuff, that the file is being, for example, deleted in this example that we gave. But we also have the USN journal, and USN stands for update sequence number, which is kind of a more high-level journal that keeps some sort of why information, why this operation is happening to begin with. So this might say, I was in the middle of copying, we'll do a copy of X blocks from here to there because a new file was created, for example, or a file was copied. And this is a very useful journal because it also assists us in creating realistic timelines of the events that were happening in the system. Now, if you remember before, we talked about the idea of modern disks keeping the metadata kind of closer to the data, okay, in these groups, because it allows for efficient seeking, okay. So ext3, going back now to Linux file systems, has this idea of block groups, okay, and these block groups kind of are preceded, let's say, by the super block, which is a special block that in there has, for example, the metadata, like how many blocks in the block group, and other the state of the block group, and other metadata, important metadata. Now, these super blocks have a certain signature, again, like a certain magic number that identifies them. So if you look, for example, in the disk and you start seeing EF53 at certain expected offsets in the disk, then you know you've probably found the super block. And then, because when disks fail and they start having what's called a bad block, like a part of the disk starts failing, it tends to also affect the other nearby parts of the disk. So you can imagine a magnetic disk that starts to get demagnetized in an area for some reason, because maybe, for example, someone has placed a big magnet on top of the disk. So one area of the disk is slowly getting demagnetized, right? Therefore, nearby blocks are going to be affected. That's why the superblock allocation algorithm copies the superblock further down and further down on the disk. So if this bunch of blocks start being bad, it will be able to first traverse, for example, 8K further down, or 16K or 32K further down on the disk, and find a copy of the superblock so that it can recover the state even if that part of the disk has been damaged. Now, how do we mount a file system, and what is mounting? Mounting allows us to access file system as if it is now on a local disk in our computer, right? And see the files on it, and start, operating on the files and operating on the metadata and all that stuff. Now, it is important to note here that typically when we get access to a file system, especially for forensic purposes, we shouldn't mount it, because when we mount the file system, we start changing the metadata in that file system. Okay, there are other ways to examine it, in a post-mortem fashion, like, statically, without actually mounting it. But sometimes, if we have kept a copy of it, we might want to mount it for ease of use, right? But typically, we should generally mount the file system with an option that is read-only, so we don't actually, by mistake, write something on the file system and change the contents. Okay, and here I'm showing you another name of an option for Linux called loop. So if we actually have not a real device, but like a file and a capture that we have in that file, a capture of a file system, then we need to use the -o loop option. Some systems might recognize it, figure it out by default. So even if you don't put that, they will figure out the right thing to do. But it's good for them to specify it as an option. And then we give a directory that we want the file system to be mounted under. Also, typically the mount command is a privileged command that should be used by the root user. If we want to stop having a file system in a mount state, then we can use umount to unmount it. You can see this video for more information on mount. Now, how does it work, mounting? Of course, it needs to populate the directory entry, right? Because then we'll go under the directory and we'll see files. So, and also when we're in the parent directory of the mount, when we need to kind of start going to an inode that is a special inode. It is now on a new file system. So there are these dynamic inodes that are being created that point to another device, and that other device has a different file system. Okay, and of course you should pay attention here, because every file system has its own set of inodes, right? So inode number 34 makes only sense under the scope of the file system that it is under. If we go on another file system, inode number 34 might be a completely different file. Okay. Now some limits here, just for you to see how selecting a block size can affect the total, for example, maximum file size that we can have. So, for example, if we select a block size of 1 kilobyte, okay, in an ext3 file system on a 64-bit machine, we can have a maximum file size of 4 terabytes, while if we select a block size of 64 kilobytes, we can go up to 256 terabytes. Okay. And this also tells you the sizes of the metadata structures here, like for example the block maps or the block group size and all that stuff. Okay, how many inodes per block group, etc. Now, think about it. Like, you have just plugged the USB drive, for example, in your computer. You have mounted it. You're doing stuff on the file system, like copying files or changing the ownership of files, or generally affecting the state of the file system, and then you just unplug the USB without unmounting it. The file system could be at a corrupted state. Okay, and a lot of times when we deal with forensics or data recovery, we have to deal with file systems that are not in their happy state. They are somehow corrupted because the power went off, because we dropped water on the computer and turned off, and now we need to recover the data somehow. So knowing how to recover data and how to actually use all that useful metadata data structures that we saw before into performing a file recovery is part of forensics. So in Unix there is this program called FSCK, and here are some useful options, and you can check that video out where we dive deeper into how to use FSCK to recover data from a file system. And now you kind of know what it will try to do. Like, for example, we'll try to find the superblock, see the state of the file system, see the dirty bit there if it's set. Okay, if it was not unmounted cleanly, then maybe it will check the journal and see what was going on, and if it can fix the state of the last operation that was happening, and so on and so forth. So check out that video for more info. And on Windows, what is the correct way to deal with corruption? Again, we have the fsutil repair subcommand now, and we can see if there are any logged corruptions on the system, and then we can actually repair them. Okay. Again, we're going to talk more about Windows on a completely different lecture. Now, finally, I would like to talk about acquisition tools, and we have been using dd'ed until now, which is fantastic. But a lot of times, as we said, on an actual investigation, you extract the data and then you want to pass it off to someone. You also need to hash the data to start, to lock the state of that data with a hash at that given point. Then we talked about problems in hashing, and we said that maybe you need to do two different types of hashing and provide checksums of two different types along with it. Well, there are tools that actually do that automatically for you, not just the hashing, but other stuff too. So let's talk a bit about certain tools. Here we have DCLFDD, which was from the forensics lab at the Department of Defense at some point in the late 90s, I think it was created. So this can hash data as it appears, and split the data, but also at the same time it has options to overwrite with random patterns and all that stuff. Now, I think this tool is a bit dated these days, but we just mentioned here as a similar to dd'ed tool with extra features. Then if you are on Linux and you want a graphical user interface type of program, then you can use Guymager here, and it can output certain different forensic file formats that I'm going to talk about in a second. And on Windows, you have the FTK Imager, which is a commercial program. I think there might be like some sort of shareware option, but this can also parse a bit into different types of file systems. It can do like also basic file and delete, and it's a pretty nicely packaged tool. Now, of course, on Linux, there is another tool that we'll talk more about called Autopsy that also does these undelete operations and all that stuff, okay, in a graphical way. So I hinted about forensic formats, and as I said, you can have a capture and annotate it with the checksums that you expect, or have a format that allows it to be split into manageable chunks. Let's say you just image the disk of a server that was 8 terabytes, for example, and you want to somehow download the data. It might not be very useful to have an 8 terabyte file that you need to download somewhere, so it would be nice if you can, for example, automatically split it. Well, there are these file system, these forensic formats like the expert witness format and the advanced forensic format. We're going to be using more EWF on this course, and this, for example, can split the big file into manageable chunks, and it can checksum individually the whole thing or just a chunk. It can support different types of captures, not necessarily just a dd'ed bunch of bytes that came out of a disk, but it could also, for example, have a memory capture or a network capture, and we're going to work with these types of captures in the following lectures. But very importantly, it also tracks things like who has opened the file, what is the investigator name, what is the case name that we're working on, and it can do chain of custody tracking, which is very important when you start having a bigger team than just yourself. And of course, it is very important to keep track of all these things if you're going to present evidence in court. Now, on Linux, you can install libEWF, which gives you access to certain tools that we mentioned here, like EWF mount, which will mount an EWF file as if it is a normal, for example, local captured image. Then EWF info is going to print information about what's happening in that capture, like for example the metadata that we talked, and EWF acquire to actually get some data and package it in the EWF format. So this is all we had for this lecture. I hope you guys enjoyed this lecture, and we'll see you next week.